In this video, we're going to be doing a Unit 7 Oscillations and Spring Energy FRQ for AP Physics 1. Now, before we start, you can go into the description and download the PDF with these 3 questions and try to solve them yourself. So, for question 1, we have a block of mass m that is released from rest at a point A on a frictionless incline that makes an angle theta with the horizontal. Point A is at a vertical height h above point B, and the block slides down the incline passing through point B and then compresses an ideal spring with a spring constant K on a frictionless horizontal surface. So the spring is initially uncompressed. The block momentarily comes to rest at maximum compression X max. On the diagram, we want to draw and label the forces acting on the block while it's sliding down the incline. So while the block is sliding down the incline, we are going to have a force of gravity that is acting downwards from its center of mass equal to mg. And we also are going to have a force that is normal, perpendicular to the incline at 90 degrees from the point of contact. So because we know that this surface is going to be frictionless, that means that we have no force of friction acting. Now, because this force of gravity is not on the exact coordinate system of y and x, we're actually going to adjust our incline to have a axes that align with the incline. So we have this. So we're going to split up FG into a vertical and a horizontal component. We're going to have this vertical component here. This will be mg cosine of theta, and then this will be mg sine of theta for your FG x component and for your FG y component, because this will be your angle theta, and we can label this side as your hypotenuse. This is your adjacent side, and then this is your opposite side from angle theta, which is how we get those relationships. Now, we can take our forces that are in the perpendicular direction to our incline and set that equal to 0. We have that our normal force acts upward, and we have a mg cosine theta force that is acting downward that's equal to 0. So our normal force is equal to mg cosine of theta. Now we can take Newton's second law parallel to the incline as well. So our forces in the parallel direction are equal to ma. And in the parallel direction, we're actually going down, so we're going to say that's equal to ma. We only have one force that's acting. That's going to be our force down the incline, which is our horizontal FGX. So that's equal to mg sine of theta. So if we just isolate for our acceleration, we can cancel out m on both sides, and then we are going to get our acceleration is equal to g times sine of the angle theta. Now, for our second part, we're asked to complete an energy bar chart for the system consisting of block, earth, and spring for the instant just before release at point A and the instant of maximum spring compression. So our system is going to be defined as our block, our earth, and also the spring. So let's analyze each of the points. When we are at point A, we are going to have our K initial equal to 0. We are also going to have our gravitational potential energy initial equal to mg times h, and we're going to have our spring potential energy equal to 0. Now, when we are at maximum compression, this means that we are going to have our kinetic final energy equal to 0, our gravitational potential energy final equal to 0, and your spring potential energy final is equal to 1/2 of K, your spring constant, times your displacement, which is at its maximum. You're at maximum displacement because your amplitude is going to be the max. This is the furthest that you can push the block against the spring, and the maximum that you compress the spring, which is why we have the maximum potential energy, because our potential energy is going to be wanting or creating a force that is trying to encourage the spring to go back towards equilibrium. And our amplitude is always pointing towards equilibrium as well. So our sign is going to be toward equilibrium. Now, in this case, we also have no friction. So our non-conservative work is equal to 0. So the thermal energy that is generated is equal to 0. So now, for our energy bar chart, we can fill this in. This is for when we are at the instant just before point A. So before point A, we have 0 kinetic energy. We are going to have Ug equals mgh, so that's going to be maximum here when we are at point A. So starting from conservation of energy, derive an expression for the maximum compression X max in terms of mgh and K. So for this question, we want to find our x max, which is our amplitude, essentially. So we're going to use conservation of mechanical energy because we have no non-conservative forces here. So we're going to set our initial kinetic energy plus our initial gravitational energy plus our initial spring potential energy equal to our final kinetic energy plus our final gravitational energy plus our final spring energy. So we know that this is 0, this is also 0, this is 0, this is 0, and this is mgh for UGI. And we have USF, which is 1/2 K maximum, or 1/2 X maximum squared. So what we're going to do next is just multiply both sides by 2. We're trying to get our X max there. So then this cancels out. We get kx squared max is equal to 2 mgh. Now we can divide both sides by k, and we can get x squared max is equal to 2 mgh over k. After this, you can take the square root of both sides. So you get your maximum x displacement from equilibrium is equal to the square root of 2 mgh divided by k. So all our gravitational energy, UG, it is going to all become spring potential energy because we have no frictional force. And now for part D, we are asked to determine whether the answer to part C depends on the incline angle of theta. Explain your reasoning. So our answer is that no, x max does not depend on theta, and the reason is because the compression depends on our h, which is our vertical height drop, not on the path shape, which we would have gotten from theta. So we know our gravity, our work done by gravity is equal to mgh, and we know our incline acceleration, it depends on an angle, which is g sine of theta. So even though our incline angle acceleration, it does depend on theta, our total energy lost from gravity is only going to depend on our vertical height. So the energy that we lose from gravity is going to be UG. So that's going to be determined by mg delta y. So we only have vertical height here, no theta. So that means that x max is equal to the root of 2 mgh, like we saw above, over k. There is no theta. So there is no dependence on our angle. So the angle changes the acceleration and the time of our sliding. So theta changes time as well, but it does not change the total gravitational energy available. Theta doesn't change our total UG available. Now, for our next question, we have, after reaching maximum compression, this block is released by the spring and moves back toward the incline. Describe the energy transformations as the block moves from maximum compression back to point B. So maximum compression means that our block was somewhere over here and it has squished the spring as close as it can get to the wall, compressing that spring. So then after that, it's going to have the tendency to go back towards its equilibrium state where it is naturally at rest and is not acted on by a force that is restoring, because it's already restored. So it wants to go back that way, back towards B. So what can we think? Well, for part E, when you are at your maximum compression, you are going to have your kinetic energy equal to 0, and your spring potential energy is equal to 1/2 kx maximum squared. The reason is because at this point, your V maximum, your V is going to be equal to 0. And the reason is because you're going to be changing direction from a positive direction to a negative. So what that means is that if you have velocity time here, at this instant, like you would be going in the positive direction and then you would be going in the negative direction. In order to pass that, you have to pass an instance where V is equal to 0. Therefore, your V is equal to 0. So when you substitute that into your kinetic energy, you get K is equal to 0. Your US is equal to 1/2 kx squared max. Therefore, your US is at a state of maximum because you are going to have the greatest amount of displacement that you possibly can have at that point. point. And because you square it, it doesn't matter if you are in the negative, if you're maximally compressed or you're maximally stretched, because it's going to be squared, so that sign is going to be omitted. Now, because we know that the spring is going to push the block back, that means that your US is going to be converted into kinetic energy. So then when we're at point B, that means that our spring is no longer compressed. That means that you're going to have a spring potential energy that is equal to 0. So these are your two situations. And you are going to have your kinetic energy equal to 1/2 kx squared maximum, which is going to be equal to k max, because you're going to be at your natural state. And the reason is because kinetic energy is 1/2 mv squared. You're going to have your maximum v, and your displacement, your US, is equal to 1/2 k x squared. You're going to have 1/2 k times 0 squared, which is going to give you 0 for your US. And you know that all that energy has to have gone back to kinetic energy, because our total mechanical energy is going to be the same. So because we know that we have friction equal to 0, we know we have no energy loss. And that means that the thermal energy is equal to 0 that was generated. So when the block returns back to point B, it's going to have the same speed, same v, when it returns to point B. Now, for our next FRQ, we are going to have a rough surface and spring compression. So we have this block mass M that is released from rest at point A on a frictionless incline of a vertical height h. So the block is going to reach the bottom of the incline, and then it's moving across the horizontal surface towards an ideal spring of spring constant K. So then the horizontal surface from B to the wall is going to be rough this time, with a coefficient of friction of mu k. So the spring is initially uncompressed, and then the block compresses the spring a maximum distance x max before momentarily coming to rest. The distance from point B to the uncompressed distance is going to be L, and during the compression of our spring, the block is going to remain on the same horizontal surface. So that means it's not going to slide back up that incline at all. So on the diagram, we want to draw and label the forces that are acting on the block when it is moving on the rough horizontal surface and it's compressing the spring. So when we are down here, which means we're on that rough surface, we're going to have a force of gravity acting at its center of mass, which is pulling down, equal to the mass times the gravitational acceleration. You're going to have a normal force that's acting upward, equal to Fn. And you're also going to have a force of kinetic friction, because you're going to be moving, and this is going to be equal to mu k, your coefficient, times the normal force that you are currently receiving. So this is going to be opposite your direction of motion, because it always is going to degrade. Friction is going to do negative work and take away energy from our system. So we are also going to have a spring force as well, and this is going to be acting as Fs is equal to Kx. This is going to be opposite the compression direction using Hooke's law. So if we look at our horizontal surface, we're going to have that the summation of our forces is equal to 0 in the vertical direction, because the block is not going through the surface. It's only having this horizontal movement back and forth as it oscillates on this rough surface. So you're going to have a normal force that's acting upward, and you're going to have a force of gravity that's acting downward. That's equal to mg, and you're going to have your normal forces equal to mg. Now, because we know what the normal force is, we can say here that our Fn, or Fk, is equal to mu k times mg, because we have our force of our normal force. So now if we know that the block is going to move right while compressing the spring, so it's going to go to the right, or it's going to the right when it's compressing the spring, obviously, to go towards the wall. That means that the force of friction and our force from our spring are going to act towards the left, because they are going to be opposite. So that means that in our horizontal direction, we can say the summation of our forces are equal to mass times acceleration. We're going to make our right side as positive since this is the direction of our acceleration or movement. So we're going to have a negative force of friction minus the negative force of the spring is equal to ma. We just found that our frictional force is mu k times mg, and we know our frictional or our spring force is going to be kx. That's equal to ma. So then we can rearrange for a. We just divide both sides by m, and you just get your acceleration is equal to negative mu k times g minus kx over m. So then the reason why this matters is because during our compression, we are going to have that the block slows down because we have that the friction and also the spring oppose the motion. This makes sense because our friction is going to be degrading our total energy that we have available to do work, and also our spring is going to be constantly encouraging the block to go back towards equilibrium, that therefore it's going to decrease the amount of energy we have that is going to continue this movement of back and forth. So now for our energy bar chart, we are going to complete the chart for the system including of the block, earth, and the spring from released at point A to the maximum compression. So let's talk about point A first. When we are at point A, you're going to have your initial kinetic energy as equal to 0 because you're at the very top. Your UG initial is going to equal to mgh, and your spring is going to be equal to just 0 as well because you have not made contact with the spring. So now when you are at your maximum compression, you are going to have your kinetic energy final is equal to 0 because you're going to be at the maximum compression. That means that you're going to be compressed as far as you can. So your Vmax is equal to 0 and your spring potential energy is at its maximum, aka at 1/2 kx maximum squared. You're at your max displacement. Your gravitational energy is equal to 0. So then what we know is that we are going to have force of friction is going to produce thermal energy over a distance, which is the distance of L plus X max. So in order to calculate our thermal energy that we generated, that's going to be equal to the force of friction times L plus X max. That is the distance. So that is equal to force of friction we found was mu k times mg, and we have L plus X max. So then what we have on our energy bar chart, this means that as we go from point A to maximum compression, we are going to have that our UG is going to be converted into that 1/2 kx maximum squared plus our mu k mg L plus X max. So if you want to draw your initial, you're going to have a maximum of UG, and then after that, it's going to be converted into 1/2 kx max, and also thermal energy. So you're going to have thermal energy, and also you're going to have spring. So this is going to be initial, and then these are going to be your final. So write an energy equation that is going to relate the initial gravitational potential energy, the thermal energy, and the thermal energy produced by friction, and the final spring potential energy at the maximum compression. So for part C, you're going to have to start with your full energy equation. So we know we have to include the work done by friction because it was non-conservative, and we have initial kinetic energy, we have initial gravitational energy, we have initial spring energy, and we have the work done by non-conservative forces, which will subtract out. And then we have K final plus UG final plus US final, and our friction, work done by friction, is going to do negative work. So we have negative Fk times the distance that we acted on. Makes sense because work is equal to force times displacement, cosine of the angle, but we know that cosine of the angle was on it, so we don't have to include that. We're just looking at our force, and our frictional force was Ff frictional times d, and then we have work done by friction. So now here we know that our displacement D is equal to L plus X max that our friction is going to be acting and doing work on. So then our entire work done by friction is equal to negative mu K times mg times L plus X max. So now after this, let's substitute in. This is equal to 0. So we have this equal to 0 as well. We have this is equal to 0, and then we have this equal to 0. So then we can take what we have down. We have mgh, and we also have our negative mu K times mg times L plus X maximum is equal to 1/2 kx squared maximum. So now we can also rearrange this and say this is just mgh, and then put that on the other side, is equal to 1/2 kx maximum squared plus mu K times mg L plus X maximum. So we can see that our UG, it was converted into US and also thermal energy, which makes sense with our energy bar charts, agrees. Now for part D, we are asked to derive an equation that could, D, we're asked to derive an equation that can solve for X max in terms of mgh mu K L and also K. So we can start off with our equation that we have here. We're looking for X max. So we're going to distribute first our frictional term, which is this. So we are going to get mgh is equal to 1/2 kx maximum squared plus mu K mg times L plus mu K mg times X maximum. So after this, we can move everything to one side. We're going to have 1/2 kx maximum squared plus mu K mg X maximum plus mu K mg times L minus mg times h is equal to 0. So then this is going to be your expression. So you can use this, and then you can solve for X maximum. Now, if you do this using the quadratic formula, what we can see is A is equal to 1/2 K, and we have B is equal to mu K mg, C is equal to mu K mg times L minus mgh, and your X maximum is equal to negative B plus the square root of B squared minus 4AC all over 2 times A. So that's because we have our X maximum is equal to our X in this supposed scenario. So then if we have our quadratic formula, X is equal to negative mu K mg plus the square root of mu K times mg squared minus 4 times 1/2 times K times mu K mg times L minus mg times h, and you can divide all of this by your spring constant K. That is going to be our answer. And you're going to choose the positive root because our compression distance can't be negative. Cannot be negative. So the reason why, for our next part, the X max is not going to be the same as equation 1 from question 1 is because in question 1, we have no frictional force. That's because mu was equal to 0. So that's why we had mgh is equal to 1/2 kx maximum squared. However, when we are in question 2, we actually have friction. It does not equal to 0. So that means that some of our energy will convert into thermal energy. So that's why we got mgh is equal to 1/2 kx maximum squared plus mu K mg times L plus X maximum. And that friction is going to remove some of our mechanical energy. So that means we have less energy available to compress the spring. Therefore, that means that the X that you have maximally when you have the rough surface is going to be less than the X maximum that you have when you're going to be frictionless. So you're going to be able to compress the spring less of a distance if you had a rough surface as compared to a frictionless surface, because that frictional force is going to convert some of the UG into some of the thermal energy instead of our spring potential energy. Now, for question F, we are asked, suppose the coefficient of friction is increased while all other quantities remain the same. State whether X max increases, decreases, or remains the same. Justify your answer using energy principles. So we can tell that X max is going to decrease because we have from energy earlier, mgh is equal to 1/2 kx maximum squared plus mu k mg L plus X maximum. So if you increase your X maximum, which we see right here, this whole entire term is going to increase. Therefore, your US is going to get smaller. So that means that X max is going to decrease because you also have X max over here as well. So that means if you have more friction, that means that you have more energy lost to E thermal. So the spring can't compress as far. So for our next question, we have a block of mass M is going to be pressed against an ideal spring constant K on a frictionless horizontal surface. Our spring is compressed a distance x initial from rest. The block is released from rest. After releasing the spring, the block moves up a frictionless incline that makes an incline angle theta with the horizontal. The block reaches a maximum vertical height h above the horizontal before momentarily coming to rest. Later, that same block is going to be attached to the same spring on a horizontal frictionless surface and undergoes simple harmonic motion with an amplitude of x initial, x naught. So we're asked to complete an energy bar chart for the block spring earth system from the initial compressed spring to the instant the block reaches its highest point on the incline. When you're at your initial state, you're going to have your kinetic energy is equal to 0 because you're compressed to the maximum. You're going to have your initial spring energy equal to 1/2 k x naught squared, your displacement, and you have UG initial equal to 0 because we're at the very bottom. Now, when you are at the very highest point on the incline, you're going to have your kinetic final is equal to 0 because you're going to be very high up. You're going to have your spring final equal to 0. You're not in contact with the spring anymore. And you're going to have your gravitational final equal to mg times your vertical height, which is just h. So you also have to remember that you have no friction. Therefore, your work done by non-conservative forces is equal to 0. And your energy that is thermal is equal to 0, which means that on your energy bar chart, you're going to have that 1/2 kx initial squared that we have from the beginning. Your 1/2 k initial squared, that's going to convert into mg times h. So our initial state is we're going to have all spring, and then in the end, you're going to have all gravitational. So now we want to determine whether the maximum vertical height h depends on the angle theta of the incline and explain your reasoning. So for this, you're going to have to use conservation of energy, which means you have your initial kinetic energy equal to plus your initial spring plus your UG initial is equal to K final plus US final plus UG final. And notice here, because we have conservation of energy, we have no work non-conservative. So that means you don't have to add it to this side and then subtract it from your total because it's going to be the same. This is equal to 0, this is equal to 0, this is also 0, and this is 0. So you're just going to have this. Now, if we solve for just h, we have dividing both sides by mg. We have that our height is equal to 1/2 of kx naught squared over mg. Now we can see all of that US, it converted into gravitational, which makes sense. Now we're asked, determine whether the maximum vertical height h depends on angle theta of the incline, and explain your reasoning. So our answer is no, h doesn't depend on theta because our maximum vertical height, so your y max, is going to be equal to mgh is equal to 1/2 k x naught squared, only depends on our energy that we have. So that means that the incline angle, we know that that is going to change the distance traveled along the ramp, and not the vertical height reached for the same available energy. So if we say that our distance along the incline, which is going to be this, along the incline, is equal to s, therefore we can say that our h is equal to s times sine of theta. Because we have that as theta, we can relate that as your hypotenuse, this as your opposite, and then this as your adjacent, and this is as your opposite. So then in order to find h, you would just relate that with the sine of the angle theta. So we can say that here h is equal to sine theta. So if you have a different theta value, then s changes, but your y max is just energy determined. Now, for part D, we're asked, when the block is attached to the spring and oscillates horizontally with an amplitude x naught, derive an expression for the maximum speed of the block. So you're going to have that when you're attached to the spring on a frictionless horizontal surface, we still have our energies conserved, right? So when you're at x naught amplitude, you're going to have kinetic energy is equal to 0. You're going to have US is equal to 1/2 k x naught squared. Then when you're at your equilibrium, 0 displacement from the horizontal, or from your equilibrium position, your natural state. So you're going to have US is equal to 0. You're going to have K max is equal to 1/2 mv maximum squared. And you can set these energies equal because it's going to remain the same at each of these points. So E initial, which we'll define as amplitude, position, and then E final is equal to that. You have 1/2 k naught x naught squared is equal to 1/2 mv maximum squared. So then cancel out that 1/2, you get kx initial squared is equal to mv maximum squared. You get v squared maximum is equal to kx naught squared over m. So then v maximum is just equal to the square root of x naught. You can take x naught out and you have k over m for v max. So we can see that our v max is going to be at our EQM, right? Because all of your US is equal to 0 and has become kinetic energy, right? So now if we are asked, okay, for part E, we're asked to derive an expression for the period of oscillation of the block spring system. So we know that if you have a mass spring oscillator, which is on your formula, I believe, omega is equal to the root of k over m. Omega is also equal to 2 pi over the period, and that means that period is equal to 2 pi over omega. So then if you have your period t right here, you can substitute in here. Therefore, t is equal to 2 pi over the root of k over m. However, if you want to put this into the numerator, you're going to have to swap these two, and you get your period is equal to 2 pi times the root of m over k. So then let's also think about when we have Newton's second law, right? So we have that our spring force with Hooke's law is negative kx, meaning that negative is going to be a restoring force towards the equilibrium. And we have Newton's second law, summation of forces is equal to mass times acceleration. So you have negative kx as your force, that's equal to ma. Then you solve for acceleration, dividing both sides by m. You get that acceleration is equal to negative kx divided by m. And you also have simple harmonic motion where you have acceleration is equal to negative omega squared times x. So if you have here omega squared is equal to k over m, that's how you get omega is equal to the root of k over m. Therefore, you have t is equal to 2 pi over omega, right? That makes sense that 2 pi is equal to the root of m over k. So then we can see that our restoring force here is going to be proportional to our displacement. So F restoring is proportional to our x displacement. And that's why we get our simple harmonic motion. So now we are asked, a second block of mass 4m is attached to the same spring and released with the same amplitude x naught. State how the maximum speed and the period compare to those for the original block. Justify your answer qualitatively using energy and oscillation principles. So if we replace that mass, replace m mass equals m with mass equals 4m. So let's find our maximum speed. We had originally that v max is equal to x naught times the square root of k over m. So then if you have your new mass, put this under here. So this is your new mass. This is going to be v prime max is equal to x naught times the root of k over 4m. So you can take that 4 out. You get x naught is equal to, or x naught times 1/2 times the root of k over m. So then if you take the ratio of these two, you're going to have the only difference being 1/2. So the ratio is 1/2. Therefore, you can say that v max prime is equal to 1/2 of v maximum. So your v max is cut in half, which makes sense because we had from energy 1/2 kx naught squared is equal to 1/2 mv maximum squared. So if your us is the same, but your m increases, that means that your speed, your v, has to decrease in order to maintain this equality. Now, what about our period? Well, for period, you're gonna have that you originally have t is equal to 2 pi times the root of m over k. So then in your new case, you have t prime is equal to 2 pi times the root of 4m divided by k. So t prime is equal to 2 pi times 2, just take the 4 out, times m over k. So we can see t prime is equal to twice that of t. So if you have an increase in mass, then that's going to make the oscillator harder to accelerate. Therefore, it moves slower through the cycle and takes more time to complete one oscillation.